Hi, this is Klaus from electronics.unmessed. How fast can a stepper motor work? And how reliable is it? What are the penalties when the speed limits are exceeded? We will find out in a moment. The world is full of stepper motors. You find them in your scanner, printer, copier, in a 3D printer, in production machines for positioning the tools, in robots, in vehicles, and a lot more. They form an interface from the digital to the real analog world, and it's really fun to work with. Small models are usually inexpensive. That is why stepper motors are interesting for maker projects. Together with a microcontroller, you can use them for countless projects. I like to create analog gauges to display any digital values from measurements or from the internet. I think that's particularly cool because you can use it to create individually designed display instruments that you can't buy. This is always a worthwhile challenge for makers. Today we are testing stepper motors. As for almost everything in life, we have to pay attention to specifications. For example, the maximum speed, which is specified in degrees per second or in steps per second, is very important. Here are some values for the EP50 from the original datasheet. In fact, there are two different maximum speeds here. The maximum speed from standing start is 200 degrees per second, and the maximum speed with appropriate acceleration is 600 degrees per second. Incidentally, the mass moment of inertia of the pointer is also specified for the maximum speed from a standstill. If you have a moderate startup phase, you can reach a much higher final speed and you can move pointers with a larger mass moment of inertia. A startup phase or a limitation of the acceleration can be implemented using various techniques. A nice method in the case of a gauge is to apply a digital filter for this purpose. It practically limits the slope of a signal and makes the pointer move like a moving coil meter. I made some videos about the dimensioning and the properties of digital filters. I will link them in the top right corner. The second important variable is of course the torque, which ultimately defines how much power the stepper can deliver. However, in my case, I can't specify a static torque. I can actually only calculate the moment of inertia of the pointer that I want to use and compare it to the specified one above. I'm sure you already guessed that I would like to realize the pointer using a 3D printing technology. I first calculated the volume from the length, width and height of the pointer. From the density of the PLA filament material and the fill factor, I can then calculate the weight of the pointer. It's about 0.17 grams for my 8.8 cm pointer. I neglected the inner part and the tip of the pointer for this calculation. The mass moment of inertia results from the square of the length times the weight divided by 3. It is 4.39 times 10 to the minus 7 kilogram and square meter. Since I have designed a relatively large pointer for a large gauge, the moment of inertia in my case is about twice as large as given in the specification above. Okay, that tells me that I can't operate the gauge at 200 degrees per second. It certainly needs to be less than 100 degrees per second. In my control software, the maximum angular velocity is defined using a delay. 8333 microseconds per step corresponds to an angular velocity of 60 degrees per second. I've learned from a few tests that I'm on the safe side with that value. So, as we can see, rapid changes in speed are not the great strength of stepper motors. But the X27 is particularly interesting for building analog display devices. It is optimized for speed. An internal stop can be approached because its torque is low. It therefore doesn't need a separate logic with a limit switch or a Hall element. The stepper motor X27 can be controlled directly with an Arduino board, as it draws less than 20 milliamperes of current. We would now like to know how quick and reliable this combination works. That's why we are testing exactly this for many hours. We analyze if the stepper motor lost steps after many chaotic back and forth commands. We do a long-term test with acoustic signals. For most applications, stepper motors operate at a relatively constant speed. They execute commands like turn 1542 steps to the right or turn 42 steps to the left. Then the stepper should be in position 1500. I have a job here that is quite stressful for a stepper motor. I give a very volatile acoustic signal to the control unit. As you can see, the pointer has to make completely chaotic movements all the time. Sometimes the movements are long, sometimes short, sometimes fast, sometimes slow, and then the direction keeps changing. We would like to know whether the stepper motor loses steps in this test. At regular time intervals, we drive the stepper to the value 50% to see if the stepper has lost steps. In case this value is no longer approached exactly after a while, then some steps are lost. We let the test run for several hours now. And the results are really interesting. As long as you stay within the specified speed, the stepper works extremely precise. Even with these chaotic movements, the stepper does not lose a single step even after hours. That's remarkable. Things are very different if you try to run the motor faster than it is specified. Then a relatively large number of steps is lost. If you want to drive significantly faster than the specification, then the stepper reacts completely uncorrelated and is of course unusable. A stepper motor should always be operated within its specifications. The mass moment of inertia of the motor and the mechanism to be driven should be taken into account for the calculation of the maximum acceleration and deceleration. The motor doesn't take any damage, but anyway, everything else doesn't make sense. If you stay within the specification, then it works with any arbitrary signal. So, now we can continue with our small project where we want to build an analog display instrument with a stepper motor. See you in the next video. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.